So in the last segment, I laid out what Quantivo considers to be its requirements for software as a service in the cloud. I mean, for an analytics software as a service offering. As I mentioned before, in our mind, when we built this thing, we architected it from the ground up to be a software as a service solution, but we wanted it to be a software as a service solution with little or no compromise in terms of the data sizes that could be managed and the type of questions that could be asked. What really underlies all of this and enables it, in my mind, is some very, very novel technology that we have, patented technology around how we process and store the data. So the core technology we have, we call it a Q-tree. Fundamentally, it is a different physical architecture for storing data, again, based on the patents that we have. And in this installment, I'm going to walk through, admittedly, what is a toy data set, but I'm going to walk through, in a step-by-step basis, at least logically, how that structure is built. And I think from seeing that, it'll become pretty clear the benefits to the technical approach that we have. So this is an example. This is admittedly a toy data set, but it is pretty kind of typical of what you see in transactional or event-based data logs, meaning web-type data, retail data. And what that is that there tends to be a lot of redundancy at the column level and then a lot of uniqueness across the transactions. And so what our core technology does is, based on a tree-based definition of the associations in the data, we start with a technical approach that some other systems have done before, particular column store databases, where we start on a per column basis. What we do is we look at the data that's in the data set, and we look for redundant patterns initially at the column level. So in this example, what we're saying is that for home.jsp, we've seen that value once, and what we're doing is we're creating a dictionary of those values. We're doing a token-based substitution of those values, which is very similar to the compression algorithms that underlie gzip or winzip or anything that you might use. We do a token-based substitution here, and then we count the occurrence of that primitive value, as we call it. And we do that across the entire relation. So for distinct user IDs, distinct times, I'm considering this to be time on page. And then for distinct dates, we count the occurrences that we've seen of that. We do the token-based substitution, and then we count. But unlike other technical approaches based on this tree-based structure, what we also do is we roll up the associations in the data. So the leaves, if you will, of the tree record the column values, but the nodes in this tree record how often these values have occurred together. So what this node is basically recording is that home.jsp and this user ID have occurred once together. And again, we do the same trick here. We do a token-based substitution here, and then we count the values. We do this on this side of the tree, if you will, as well. And then rolling all the way up to the root node, as we'd say, of the tree, which at any given time is always the full relation, if you will. And that's why this is a lossless approach to compressing the data, because at any given time, you can always recover the full relation, if you will, from the root of the tree. Now, the benefits to this approach are already you're achieving a good amount of compression in many cases just by doing this token-based substitution. But you can see how, in theory anyway, the approach could be almost perfectly compressive if you have redundant data. So this is an example. It's obviously a very trivial example, but it's an example where one event or one row from one to the next in this data set is an exact duplicate of the previous one. And what you see in that case is pretty much perfect compression, because literally in that case, all we would do is just increment counters. Incrementing counters doesn't increase either the on-disk or in-memory data size of what we're storing. So we're storing all the data, but the one way we talk about this quite often is that this data structure is going to grow relative to the size of the information, not the data itself. But this is obviously kind of a trivial example, but where we achieve many factors of compression that is possible in other approaches is that the structure really takes advantage of localized, if you will, areas of compression in the data. So in this example, what we see is that, if you will, on the left-hand side of the tree or the left-hand side of the data stream, there's redundancy there. And again, no new homepage, no new user ID, so we increase counts here. And there's kind of no new information at this level either, so we're just increasing counts. But on the right-hand side of the transaction, if you will, we have a new time on page, which creates a new entry in this dictionary, which creates a new relation here or a new association here, and then it creates a new association at the top of the tree. And so it all kind of rolls up that way. New information is recorded here, but any redundant information is not really recorded here through the top of the tree. And then you can see that the algorithm kind of proceeds from there. This is an example of a new user ID on that home page. Again, so now the left-hand side of the tree, if you will, is growing a little bit proportionally, and then new data on the right-hand side as well. So the right-hand side of the tree as well. But again, what you're seeing is that the size of the tree, both on disk and in memory, is growing more proportional to the information in the system as opposed to just the raw row counts of data. And then the last example here is again just a perfect kind of duplication of the previous record. And so again, we're just incrementing counters. So this is a highly naturally compressive way of storing the data. We're storing it just in terms of unique patterns. But the first point to make is that it's not compression just for compression's sake. It's not just gzip or it's not just winzip compressing the size of the data. We are storing the data, if you will, already in a very highly analytic format. You could almost think of each of these nodes as already pre-aggregations and pre-summarizations of the data, again, without losing any detail. And then in particular, what we have in our data structure is we have pointers that point in both directions of all the data, from all the nodes in the tree. What that means is that although you might have a topology to the tree that stores certain relations or certain associations and compresses a certain way, we can always, on the fly, reaggregate or requery if we need to kind of answer any question against the stored data. So in this example, you would say, for instance, that page name, the association between page name and date has not been pre-computed, but the relation, if you will, is still maintained through the root node. So if we need to, we can re-aggregate by going to the root node, recovering data, and aggregating on the fly. And then the important point there, too, is that we are doing all that query processing over highly pre-processed, highly compressed data, and we are leaving the data that compressed as we do it. And that's where we achieve a lot of our performance benefits at 10 to 100 times faster than a comparable approach in a relational database, for instance. So that's really kind of the core of what we do and the highly different way that we store the data. Again, we work completely over compressed data, and what we also have is we have the ability to tune the system in many ways as well. So what that means is that in many cases what we tend to do is we'll create one tree that will encompass all the data and compress all the attributes in the data. But just like an indexing strategy in a standard database, we have the ability to create redundant reprojections or multiple reprojections of the data, so other trees that have the same attributes but have a different physical topology. Because in many cases, especially for very large data sets, the performance of queries will actually be gated by the cardinality of some of these intermediate nodes. And if you have many attributes, and we have trees like this that have 60, 70, 80 attributes in it, and if you have billions of records, which we have trees that have that as well, the root node, and in many cases some of the lower nodes, get very close to root cardinality. They get close to, there's billions of points of information here. So the query performance can be gated by your ability to go through these nodes, and in those cases, if you want to re-index and create different trees with different kind of combinations of associations, we allow that in the system as well. So we have the ability to do base level queries that are very fast, but then also have an indexing-like strategy and put more trees in the database, if you will. And that's really how we get our performance benefits, but doing it in a way that doesn't balloon I/O, so it scales very well in the data center. I hope this makes sense to people. Again, I think this is a logical definition of how we do this. There's lots of details to how we physically store these nodes, and we actually squeeze extra compression out of how we store them. But I think this really paints a picture of the fundamentally different physical way that we store the data, and it's the basis of our performance improvements and our ability also to scale within the data center. All right. And in the next installment, I'll talk about how we leverage this technology into a fundamentally different architecture that works in the data center and provides all the benefits that we talked about. Thank you.